Okay, let's talk about breaking and making bonds, all right? So think about a stick. Think about the game Red Rover, if you've ever played that as a kid, where you have to run across and break through someone else's arms. Think about football, where someone has to break a tackle. If we're breaking bonds, if we have to break something, it requires energy. You have to put energy into something, okay? So you are absorbing energy. Energy requires energy to be absorbed. It's endothermic. You're gaining energy. So whenever you want to break a bond, you need to put energy into that to overcome those attractive forces that are occurring between those atoms, okay? When you want to make a bond or form a bond, that is where you release energy. When you are creating those bonds, you are actually at a lower energy state. It's becoming more stable, and the energy that was stored up in those atoms, if they were already broken, are now then released, so then they can bond with another atom. So that's exothermic, and it loses energy. So what you are going to be given a lot of times is this chart. It's a chart of bond energies. And I want you to just focus on a couple quick things, is looking at doubles versus triple bonds versus single bonds. So if you look at carbon, it's 347, but a double bond is 614 and a triple bond is 839. Clearly, as you add more bonds, there's more energy in those bonds as a requirement. So you have to break the single to the double to the triple with extra energy, because you're overcoming additional attractive forces because there's more electrons involved, okay? So here's the equation. And it looks complicated, but it doesn't need to be. It's the change in H, which is enthalpy, which is energy flow. And it's basically the sum of the moles of your bonds that you break. D is just a representation of bonds. And then we're going to subtract the sum of the moles of the bonds that are made. So this is not products minus reactants, which most students do. Products minus reactants is when you have the enthalpy of formation of each of these already. They're already been made. The bonds have already been broken or formed. This is starting with compounds, breaking those bonds and then making them. So I always like to think of it as you got to break them before you make them. Okay? So you've got to break the bonds, then you got to make the bonds. So let's take a look at a really cool reaction. You've seen this before, it's the whoosh bottle. So let's take a look first.
Wow, awesome.
What we have is an equation, and it's methanol. It's combustion of methanol. And an important thing with all of these is your understanding of what the molecules are structurally. You know, what are your Lewis structures? So when I look at methanol, I have to have an understanding of what the bonds exist. So my bonds would be a carbon bonded to 3 H's, right? And then an oxygen to another H. My oxygen is actually a double bonded O. My carbon dioxide is 2 double bonded OCs or COs. And then my water is a single bonded to 2 different H's. Now, some people like to write this 3 times. I just want you to realize that this 3, for example, means that there are actually 3 of these. Now, I'm not going to do that only because I don't really want to draw another one of these, and then I got to draw 4 of these. But just realize that these coefficients still matter. So what we're going to do is break this down first in just the idea of what do we have present in bonds. Okay, so first, let's break bonds. Breaking bonds means these. I got to break every one of these bonds right here, okay, before I can make all of these bonds. All right, so we're going to do brackets. So what I have is I have an CH bond, right? But I have 3 of them. So here's 1, 2, 3, but then I have 2 of these compounds. So anything I add in here, I have to multiply by 2. So I have 6 CH bonds. What else do I have? I have a CO bond. So I have 2 of those because there's 2 methanols. And then I have an OH bond, and again, I have 2 of those. Okay, so that takes care of my methanol. But I still have oxygen. So what I have to do is I have to break 3 of those double bonded O's. Okay, so those are the ones I'm going to break. Now I'm going to subtract. And the reason why I'm subtracting is because it releases energy. When you make a bond, you release it. Okay, so let's take a look at what I have here. I have 2 CO bonds, C double bonded O's, but I have 2 of these. So I should have 4 of those. And then I should have an OH bond. I have 2 of them in water times 4. So I should have 8 OH bonds. This is a really nice way of laying it out. Okay, so now let's actually calculate it. So I have 6 times my CH. Here it is right here to the right. CH. I'm going to highlight these so then I can keep track of them later. So it's 413. And it's going to be kilojoules. There is not a label on here, but they are kilojoules. 2 times. See how organized this is? Now I can just look up and find what I need each time. A CO bond. So I find carbon and oxygen. There it is. 358. All right, now I need an OH bond. So I'm looking for it. There it is, 467. I have 2 of those. And then I need 3 double bonded O's. So I'm going to go over to the double bonded area in this case, and 495. And I always write kilojoules at the ending of this first part. Okay, so those are the bonds that I'm breaking. The energy that is required to break those bonds and the number of bonds, moles of bonds that I have. Now I need to subtract the bonds that I'm going to create. So I have 4 of my C double bonded O's. Now, this is where some students make a mistake. You see C double bonded O on some tables, you'll see a value, and if there's an asterisk, you need to make sure that you're paying attention. Now, in this case, this is CO2. But if you were like dealing with a carboxylic acid, a C double bonded O, so something like this, and so on and so forth, that is not a carbon dioxide kind of bond, so I would actually use this one instead. But in this case, it is 799. So I need to use the 799. Okay, and then I need to find my OH again. Now, I have already done that one before, 467. Please do not get fancy and go, oh, wait a minute. So if I have 8 on the right and 2 on the left, I can create 6 somehow. Just write them down. Show what is being broken. Show what is being made. All right, so now we calculate that all out. It is a good idea to show the energy that is required to break the bond. So if I add that up, it's 5613. And then the energy released is 6932. So my overall enthalpy of this reaction is negative 1319, which should make sense. It is releasing energy. Looking at that reaction, it definitely releases energy. So that is how we deal with bond energies. It is bonds broken minus bonds formed.